Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. In 1610, using a telescope of his own design and manufacture, famed Italian astronomer and polymath Galileo Galilei would look up at the night sky and observe things that would forever alter the trajectory of his life, the field of astronomy, and humanity's understanding of the universe and our place in it. In addition to refining Copernicus's heliocentric model, his observations of the Moon, the Sun, Jupiter, Mars, and the Milky Way challenged centuries of dogma and placed Earth on equal footing with the other planets of the solar system. Galileo's influence would be so far-reaching that it would extend all the way to the 20th century in the development of advanced theories such as relativity. I'm Matt Williams, and this is Stories from Space.
Welcome back to another episode of Stories from Space. I'm your host, Matt Williams. And today, I want to dedicate this episode to one of the most famous household names when it comes to astrophysics, astronomy, and cosmology, and that is none other than Galileo Galilei. In many ways, this episode is a continuance of a previous one, which was about the Copernican revolution in astronomy. A revolution, that is, where Copernicus represented the synthesis of knowledge that had been around since classical antiquity, and throughout the Middle Ages, there are many people who added to the development of the heliocentric model of the universe. And since then, it's been refined many times by many different scientists. But Galileo played what is arguably one of the most important and crucial roles. He not only took the Copernican model of the universe and showed exactly why it worked, he introduced new observations and things that no one had ever seen before, and used these to effectively demonstrate what has come to be known as the Copernican principle. It's that we are not special or unique in our position in terms of our observations of the universe. We are all subject to relativistic observations. The very term relativity owes its existence to principles he argued, and so his influence would reach well into the 20th century. His pioneering work on gravity would eventually lead Newton to his theory of universal gravitation, and to this day there are people who owe their inspiration to Galileo and the kind of arguments he made and the way he went about proving the scientific method. So to illustrate what is arguably one of the most important principles or axioms there that Galileo argued, there's the Galileo's ship argument. And what it states is that basically if you are standing on the deck of a ship at sea, and you had no landmarks around you, no means of judging how you were moving, and you were traveling at a consistent velocity, you would be barely aware that you were moving at all. And in fact, if it was pitch black out and you saw lights drifting by, you wouldn't be able to tell if you were moving or they were moving relative to you or what. And if you're both moving, that throws off your perspective even more. It's only by factoring in your own motion and speed that you can determine the motion and speed of other objects. And this was how he was able to explain to people in common sense terms, in basic logic, how the Earth could be moving and how this affected our perception of the cosmos without us being aware of it. So for this part of the Galileo ship argument, he stated that imagine that you are standing on the deck of a ship. It is at sea, it is moving, and you have a ball in your hands, and you just drop it straight down towards the deck. Now to yourself, that ball looks like it's falling straight down. And if you move the ball over to the edge of the ship and drop it there, then the same effect happens. It looks like it's falling straight down. But to an observer on the shore who's watching you move ahead and playing with this ball, that ball looks like it's falling in an arc or a parabola. Basically, it's moving forward as it's falling, and it's tracing a path. This effect is easily attributed to the fact that, well, it's moving forward with the same speed as the ship, and it's also falling because gravity's pulling it down. Point is that the ball is behaving this way because it's part of the ship's moving reference frame, or inertial reference frame. And, as I said, for the person standing on the deck, because they're part of it too, they're not aware that they're moving. And as long as they're traveling at a uniform speed, if they accelerate, they'll realize they're moving, they get pushed back. But otherwise, the only way that they would be aware of that they're moving is by looking at landmarks, which gives them a sense of which direction they're moving in and how fast. And this, Galileo argued, was the same with planet Earth. It's rotating very rapidly, it's orbiting around the sun, but because we're part of that inertial reference frame, we don't feel like we're moving and we don't suddenly fall over. This argument was crucial to his defense of Copernicanism and his explanations of how the universe really operated. And these and other arguments he would formally present in his magnum opus, which was released in 1632, and it was titled Dialogue Concerning the Two Chief World Systems, in which he argued and demonstrated how Copernicus's heliocentric model was the winner over the older geocentric model, which was based on the arguments of Ptolemy and Aristotle, and was considered canon and was also sanctioned by the Church. Now, to give you a sense of the problems that the geocentric model presented, and these were the same problems that Copernicus sought to address with his heliocentric model. They were issues that plagued astronomers going back to ancient times and classical antiquity. Essentially, astronomers who had been cataloging the positions of the planets in the night sky and their motion over the course of centuries and millennia, they were hard-pressed to explain why, periodically, planets like Mars and Jupiter, they would appear to slow down in their movement through the constellations in the night sky over the course of, depending on their orbital period, a year or several years, why they would slow down, reverse course, then resume course back in their normal direction from west to east, and speed up again. Ptolemy had attempted to resolve this by saying that, well, you have epicycles. The planets rotate around Earth on one wheel, called the deferent, and then they rotate in place on an epicycle, so wheels within wheels. And that was meant to explain why it looked like the planet was reversing course. It was simply going around in its circle, and this was also meant to explain why planets would appear closer to Earth, which is to say they were larger and brighter in the night sky at certain times of the year than others. Now, this was meant to explain all that, but unfortunately the math still didn't work out. And also, Ptolemy was hard-pressed to explain how planets could do this, yet still maintain perfect circular uniform motion, from which he introduced another argument called the equant. It's like, well, the equant's a point that lies between Earth and the body orbiting, and if you measure its motion from that point, it will be uniform, but back here on Earth, it appears as non-uniform. So these arguments were seen as a way to save the traditional classical dogma that stated that, the planets rotated around the Earth in uniform circular orbits and did not deviate from that. Galileo would address all this in his dialogue concerning the two chief world systems, and it was this dialogue that would ultimately get him into trouble with the Vatican and lead to his house arrest, where he would live for the remainder of his days. But the build-up to that is something that is also very fascinating and really requires examination. So to give a very brief summary of Galileo's life, he was born in Pisa, in Italy, in 1564, and his family was technically part of the aristocracy, but they were short on cash. And he moved to Florence, the entire family moved to Florence in 1574, and Galileo began to be tutored and educated in the monastic tradition, but also his father, who was a very talented musician, wanted him to study medicine and become a doctor, so he was encouraged to go to the University of Pisa. He did exactly that. He pursued a liberal education that included the arts, medicine, and theology, but was very drawn to science and engineering from an early point. So, Legend has it that he accidentally attended a lecture on geometry and then made the decision to switch to mathematics and became an inventor to make money to help his family pay off their debts. And by 1589, he became the chair of mathematics at Pisa. His father died 2 years later, which then left him in charge. So then he began lobbying for a more important post and transferred to the University of Padua, where he taught Euclidean geometry and mechanics and astronomy, right on up until 1610. And it was at this point that he began to make immense discoveries in the field of astronomy and what are his most enduring contributions to the science. Even though he presided over several other impressive inventions there during his time as a student and during his time at the University of Padua. Several of his inventions had important military applications. In 1609, though, he began researching telescopes because he had learned of a Dutchman who had shown a telescope of their own making in Venice, and enamored with the possibility of using this to conduct observations of the heavens, he decided to school himself on how to make them. And he also learned how to grind and polish his own lenses because glass quality at the time was an impediment to making clear observations. And so before the year was out, he managed to develop a number of different telescopes, which he got a chance to present to the Senate in Venice. And he eventually reached a point where one of his telescopes had a resolution power of 20 times normal resolution. And that was unprecedented for the time. And he was able to market this idea, saying that it had plenty of commercial applications, not the least of which were for ships at sea. But he reserved one of his telescopes to make observations of the heavens that he would then record, and in 1610 he got to work on that. And these observations became the subject of his first tract that he published on astronomy, and it was called Sidereus Nuncius, or the Starry Messenger. So, as he recorded in this booklet, he conducted observations of the moon and its lunar surface, of the Milky Way, the background stars, and from which he was able to discern patterns that astronomers would later recognize. He recorded sunspots, and also how Jupiter had its own system of moons. Now, all of this was very, very interesting, but the implications of it went far beyond merely recorded observations. Effectively, he demonstrated, with observing the moon, that there were changes in elevations, and he made topographical charts and illustrations, as well as features on the surface that included all these craters. From that, he was able to argue that the moon actually has features the way Earth does. It's not a perfect sphere. And this was something that was very much in keeping with classical and Christian dogma, Aristotelian theory, and Ptolemaic theory that said that the planets are perfect crystalline orbs and they move in perfect circles around the Earth. So this was one of the first nails in that coffin. When he turned his telescope towards the sun and began recording what the light looked like by shining the light coming through his instrument onto a piece of paper, he noted how there were spots. And these spots couldn't be explained in terms of imperfections in the lens because they kept showing up, and they appeared to be rotating. So from that, he was able to show that, well, the sun has imperfections too, aka sunspots, and that it is also rotating. And the idea that Earth itself rotated was something that astronomers had been dealing with for quite a while. It was how they could explain more effectively the motion of the stars in the night sky. The stars weren't part of some large sphere that moved around the Earth, but Earth rotated, creating the illusion of the stars moving. So Galileo also turned his telescope towards background stars, and he was able to note by looking at the milky spots in the night sky. These were not nebulas or cloudy regions so much as densely packed star clusters. When he looked at Jupiter, he recorded some observations that were especially interesting, which showed that it had stars that appeared to be orbiting it. At least that's what he initially mistook them for. And so over the course of several nights, he observed these so-called stars, and he noted that not only were they changing position, but at one point, one of them disappeared behind Jupiter's big, bright disk. And so, at that point, he realized, those aren't stars, they're moons, and they're orbiting Jupiter. So once again, all of this together put several nails into the coffin of the geocentric model and the notion that the heavens were perfect and that they were differentiated from Earth, which was base and material. As I said, that was very much keeping with Christian dogma, the separation of heaven and earth. Galileo essentially demonstrated that the heavens and the earth are very much the same in several respects. And another thing he was able to prove, and Copernicus himself had argued this, was that the stars are much farther than initially thought, much farther than the geocentric model argued. He argued this because, well, they would have to be, because, as he indicated, it is impossible to do parallax measurements with stars, the way that one would do with planets. You measure the position of a planet in the sky relative to where you're standing on Earth. At different times of the year, you're able to basically obtain distance measurements to it. But one could not do that with stars, which in Copernicus's mind confirmed that, yes, the planets are moving, and the background stars don't change in appearance because they're really, really far. So Galileo was able to prove that. When looking at the planets through his telescope, he noted that optical distortions, they didn't appear nearly as bright when you looked at them through the telescope, and this would lead to changes in terms of the estimate of their distance and their size. But when you looked at the stars through a telescope, it really didn't make a difference. So that, to him, confirmed that, yes, in fact, the stars are very, very far, and that's why there's no effect when you look at it through a lens. It doesn't make them appear smaller. So all of these observations were contained in Sidereus Nuncius and raised Galileo's profile considerably. Interestingly enough, the Church at the time, in the wake of Copernicus's death and the publication of this book, they really didn't react in the way that Copernicus himself had anticipated, which is why he waited until he was on his deathbed before publishing the book. But there was still controversy associated with the teaching of the Copernican model. Nevertheless, Galileo had official sanction to do this for many, many years. And from 1610 onward, he continued to make observations of Venus and Mercury, of Mars and Jupiter and Saturn, and he began to fold all these observations over into his work with championing the Copernican model. And so by 1632, he published all of these in his dialogue and explained how these effectively prove that Copernicus was correct, because any holes, any problems in the Copernican model he showed could be explained by telescopic observations. They dispelled any errors that astronomers who still followed the Aristotelian or Ptolemaic system were citing. And he would present all these arguments in the Socratic tradition as a dialogue between two people who were arguing the heliocentric model versus the geocentric model in front of a neutral observer. And the dialogue took place over several days. And so Galileo was able to put his own arguments, the arguments in favor of Copernicus's model, into the character of Salviati, who was based on a friend of his. And his opponent in this is a character named Simplicio. And the character's name, there's speculation that it was named after a 6th century philosopher who was commenting on Aristotle named Simplicius of Sicilia, but also suggestions that the name was a double entendre, meaning simple-minded, which is borne out by the fact that Simplicio makes a lot of arguments in the book that are rather simple-minded and not indicative of an education. And the neutral observer is named Sagredo, based on another of Galileo's friends, who is an intelligent and educated layman. He's initially neutral, but by the end he's brought around to Salviati's or Galileo's point of view. So in terms of the nuts and bolts, what Galileo argued was that, yes, the Earth was rotating as demonstrated through the ship at sea metaphor, and that the appearance of the planets in the sky, how that was not consistent over the course of years of observation, and how changes in the apparent size and motion of the planets in the sky could not be explained using old geocentric arguments. First off, there was the case of Mars and Jupiter and how they would appear drastically larger and brighter in the night sky during certain points in their orbital period. And the easiest way to explain this was to say that they orbited around the sun beyond Earth's own orbit. And this would explain why they would appear to slow down and reverse course in the night sky, then speed up again, because our own motion was throwing off our observations of these planets. They did not appear to move in perfect uniform orbits because Earth's own motion created a relativistic effect there. Also, he showed that when you observe Mars and Jupiter through a telescope, that their changes in appearance and brightness, they accorded with Copernicus's predictions on their orbits. And that was something that critics of Copernicus, they said that, well, yeah, Mars and Jupiter do appear particularly brighter in the night sky at some times other than others, but the level to which that changes, that doesn't accord with the orbits that Copernicus assigned. But again, Galileo was able to show that the telescope eliminated some of the brightness there, which was an optical illusion caused by atmospheric interference. Another key point he made, and this had to do with Venus and Mercury. For millennia, going back to the time of Plato and before, the fact that Venus and Mercury appeared the same size in the night sky over long periods of observation, that was seen as an indication that, yes, they revolve around the Earth, and the Sun, it revolves around the Earth as well, but beyond their orbits. And Galileo was able to completely undermine this argument by showing that, well, when you look at these two planets through the telescope, you actually note significant changes in their appearance. On the one hand, there are times of the year, or times in their orbit, when they appear to be a full disk, full bright disk, but at other times, they appear to be a crescent. And using the example of the moon, he was able to demonstrate that this indicates that they do orbit the sun, but that they are closer to the sun than we are, and that when they are on the opposite side relative to us, you can see the full illuminated disk. When they're closer to us, you can only see part of them because the rest is shadowed. As previously mentioned, he used the ship at sea metaphor to explain how the Earth itself could be moving around the sun, and we would be unaware of it, same as its rotation, and that the moon itself did orbit Earth, but that both the Earth and the moon orbited the sun together. And, of course, how the Earth's rotation explained the apparent motion of the background stars, and how parallax indicated that they were much farther away than the geocentric model suggested. So Galileo was able to demonstrate that Copernicus was in fact correct. However, that really didn't matter because of one small passage in the dialogue where Simplicio quoted arguments made by then-Pope Urban VIII. Galileo had been asked by Pope Urban VIII to include his arguments in the book. The Pope and he were actually on good terms before the book's publication. But once he read it, he was deeply insulted by the fact that Simplicio, that the simpleton character, was the one making his arguments. And in addition, Galileo had been told that he could argue the Copernican theory, but he was not to be officially endorsing it. But from a reading of the book, it was clear that he endorsed the Copernican model, and it's the Copernican model that wins out in the end. So it was for this reason that Galileo was summoned before the Vatican and made to answer for essentially breaking his oath and insulting Pope Urban VIII, and there were threats made, threats of torture and so forth, but instead, they decided to go easy on him and made him publicly denounce his views as espoused in the book, and sentenced him to house arrest for the rest of his life. And there is, of course, the most likely apocryphal legend there that while in the town square where he denounced his arguments, stating that the Earth does not move around the sun, that he quietly said to himself afterwards, "And yet it moves." As I said, this is considered to be a legend that is right up there with Newton's apple, or George Washington and the cherry tree, or the Eureka incident involving Archimedes. In that these things did not actually happen as depicted, but they do summarize what these individuals had accomplished there. So it seemed clear from Galileo's testimony before the Inquisition and his life's work that he decided at that point, he was rather advanced in years, and he most likely believed that
the truth would come out anyway. That anything he said at that point would be seen as a compelled testimony, a forced confession, and nothing more. And he was certainly correct in that. Because, years after the Galileo's trial, heliocentrism had become the accepted model of the universe, and it would go on to be refined by future astronomers, because Galileo did actually have a few lingering errors in his Copernican model that he envisioned, and that included the fact the planets had perfectly circular orbits. However, as Kepler would go on to demonstrate, the changes in speed that astronomers would note among the planets and their distances from the sun, how that changed over time, that indicated elliptical orbits. And it was Newton who would formalize the orbits of the planets, and also he would carry on with Galileo's early work in the nature of gravity, and show how, yes, there is such a thing as universal gravitation. The same force that compels an object to fall on Earth dictates the orbits of the planets around the sun. And one other thing that Galileo got wrong was how the moon influenced tides on Earth. He didn't believe that it did, but yes, this would be corrected later on by Newton and others. Nevertheless, a huge debt is owed to Galileo, because not only did he successfully defend the Copernican model of the universe and popularize heliocentrism, which led to its widespread acceptance, his observations of the night sky with a telescope was a permanent game changer for astronomy and astronomers. And third, his method of combining rigorous observations with very clear-cut and simple logic, and his use of metaphors, these would go on to influence Albert Einstein himself, who would carry on with, he would formalize relativity in the form of a theory that could account for the laws of electromagnetism and reconciling them with Newton's theories of motion and gravity, and create relativity as we know it today. A very complex theory which just happens to explain how matter behaves on the largest of scales with incredible accuracy and predictability. To once again quote Newton, who said that, "If I have seen farther, it's because I stood on the shoulders of giants." Well, Galileo is absolutely someone who not only stood on the shoulders of giants, but provided so many future scientists with a very, very firm foundation from which to further develop his theories and other theories that scientists have been working on since. But of course, this is why his name is so very synonymous with the heavens. It's also why Jupiter's largest moons are named in his honor. Io, Europa, Ganymede, and Callisto, which he discovered, are now known as the Galilean moons. And the NASA probe, which explored Jupiter's Galilean moons between 1995 and 2003, was named the Galileo mission in his honor. The recently launched Galileo project, which is being spearheaded by Professor Loeb of Harvard University. This project is now going through the volumes of declassified UFO sightings to determine if any of them may have actually been alien spacecraft. Also, the United Nations decided that the International Year of Astronomy should fall on 2009 because it coincided with the 400th anniversary of Galileo first looking through his telescope at the heavens. The EU issued a €25 coin with Galileo's face on it to mark the occasion. And in the city of Florence, his old homestead, there's a museum that is dedicated to him, his life, and his achievements. Needless to say, Galileo may have gotten a raw deal in his own time, but history remembers him as one of the most brilliant, insightful, and influential scientists of all time. This has been Stories from Space. I'm Matt Williams. Thank you for listening.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.